Hello students, Professor Nugent here. In this video, we are going to derive the ordinary least squares estimators. Our goal is to estimate beta naught and beta 1 using a random sample of data on observations or on variables xi and yi for observations I equals 1 through n. All right, so we have two variables, x and y. X is the independent variable, y is the dependent variable. We have observations 1 through n, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way through n, okay? We are going to model this relationship, this linear relationship between x and y. And an example of this is the relationship between education and wage that you see here on this plot. We have a sample of data and we want to see what is the best fit line to represent how wage changes for changes in education. So this line that you see here on this plot might be the line that is best fit. So we want to see what are the parameters that are going to give us this line of best fit. Beta naught, that's the intercept of wage when education is 0. Beta 1 is the slope of this line. So we're going to derive the ordinary least squares estimators, which are the values for beta naught and beta 1 that give us the line of best fit between education and wage, or any sample of data. So what we're going to do is we're going to begin with the population moments that we wrote down when we defined our simple regression model, and that is that the expected value of u is equal to 0. And we also started with the zero conditional mean assumption that the expected value of u given x is 0, which implies that the covariance between x and u is 0. We can rewrite u as y minus beta naught minus beta 1 times x. So plug in the regression for u, and that still equals 0. Likewise, for the covariance between x and u, that is expected value of x times u, we plug in the regression, the right-hand side, this value for the regression in for u, and we're going to work with these population moments, replacing them with their sample counterparts. And then we're going to solve for the values of beta naught and beta 1 that solve these equations. So these two are the sample counterparts for these two population moments, 1 over n times the sum from I equals 1 to n of yi minus beta naught hat minus beta 1 hat times xi, and 1 over n times the sum from I equals 1 to n of xi times yi minus beta naught hat minus beta 1 hat times xi. Now observe that the first line, 1 over n times the sum from I equals 1 to n of yi, that's y bar, that's the average of y. The same for xi, 1 over n times the sum from I equals 1 to n of xi, 1 over n times the sum from I equals 1 to n of yi or xi, that equals y bar. So we can rewrite the first line as follows. Let's rewrite the first line. I'm just going to keep these last two lines down here. Let's rewrite the first line as y bar, and I'm going to put this part of the first line on the right-hand side so that the signs in front of beta naught and beta 1 become positive. Y bar equals beta naught hat plus beta 1 hat x bar. All right, what we can do then, let's rewrite this in terms of beta naught. Beta naught is equal to y bar minus beta 1 hat times x bar. And let's write this as equation, I have this in my notes as equation 9, so let's call that equation 9 for my sanity. Good. So now we have solved for an expression for beta naught hat. Okay, so this is the expression that identifies what is beta naught hat, but this is still a function of beta 1 hat, so we need to figure out what is beta 1 hat. What is an expression for beta 1 hat? Let's derive that. So what we're going to do is plug in equation 9 back into the second equation. All right, so let's do that. Let's plug in equation 9 into the second equation so that we have 1 over n times the sum from I equals 1 to n of xi times yi minus, now let's plug in this equation 9 into this sample counterpart to the population moment here for the covariance equal to 0, beta naught hat, y bar minus beta 1 hat x bar. The rest of this line is minus beta 1 hat times xi, close parentheses, equals 0. Good. Now what we're going to do is solve for beta 1 hat. And we will have derived an expression for beta 1 hat. All right, so let's expand what we have in parentheses. Let's clean this up a little bit. I'm going to collect terms on beta 1 hat and x, and collect terms on the y's, so that we have 1 over n times the sum from I equals 1 to n, xi times, let's put this in brackets. In brackets, we have yi minus y bar, and then we have plus beta 1 hat times x bar minus xi, right? So the negative times a negative makes it a positive. This one is a negative. So you have positive beta 1 hat times x bar, negative beta 1 hat xi. Close brackets, equals 0. Now what I'd like to do is take this chunk and put that on one side of the equation. This chunk, put it on the other side of the equation. Both of the chunks are multiplied by 1 over n, so the 1 over n is not going to matter for the solution of beta 1 hat because they're going to be on both sides of the equations. It's going to cancel out. So I'm going to ignore the 1 over n. So what we're going to work with is sum from I equals 1 to n of xi times yi minus y bar, that is equal to beta 1 hat times the sum from I equals 1 to n of xi, right? Because xi is multiplied times this term, xi is multiplied times this term. And now we've brought this term to the other side. So this is, there would be a negative sign in front of here, but we can multiply through and switch the signs inside this term so that you have xi minus x bar. Great. Now I want to do another thing. What we have in these two terms can be rewritten because of a neat characteristic of the summation notation as xi minus x bar times yi minus y bar. This is equal to this. Likewise, beta 1 hat times the sum from I equals 1 to n xi minus x bar times xi minus x bar. This is equal to this because of a neat thing with the summation notation. Now all we have to do is solve for our beta 1 hat. So we're going to divide through by this. Note that these are the same terms, so that becomes a squared, and I'm going to divide through by the sum from I equals 1 to n xi minus x bar squared. Divide through by the sum from I equals 1 to n xi minus x bar squared. This becomes 1, so we can erase that, and we have derived a solution for beta 1 hat. Bada bing, bada boom. Note that in the bottom, we have the variance of x. In the top, we have the covariance between x and y. One other thing to note is that this is only going to work, this expression only works, we can only identify beta 1 hat when the sum from I equals 1 to n of xi minus x bar squared is positive. So this only works when we have some variation in x, right? We can't divide by a 0. That would not be identified. Dividing by 0 is a no-no. So if this only works if we have some variance in x, and we can plot that real quick. What are we trying to do? We're trying to look at how y varies with x, and if we have observations on x which are all the same value, then y does not vary with x because there's no variation in x. All right, folks. Great. So we have an expression for beta naught hat. We have an expression for beta 1 hat. What is next? We can take our solutions for beta naught hat, beta 1 hat, plug them into the regression equation. We get our fitted values. Fitted value y hat is equal to beta naught hat plus beta 1 hat times xi. Great. We can also get the residual, which is so we want i's on these things. Ui hat is equal to yi minus yi hat, right? So that's the residual. The residual is predicted. That's different from the error. The error is unobserved. Now, I just want to comment that we solved for the expression for the OLS estimators, starting from the population moments and replacing them with the sample counterparts, and then solving for the values of beta naught hat and beta 1 hat that make those equations true. You can do this one other way, and that other way is by minimizing the sum of squared residuals. We can solve for beta naught hat, beta 1 hat by minimizing the sum of squared residuals, or the residual sum of squares. So the sum from I equals 1 to n of ui squared, this is the sum of squared residuals, or residual sum of squares. Okay, that's what that is. And this is equal to the sum from I equals 1 to n of yi minus beta naught minus beta 1 xi, right? Squared. What we can do, we can use some dummy terms for beta naught and beta 1. Min b0, b1, sum from I equals 1 to n for yi minus b0 minus b1 times xi squared. Solve for the values of b0 and b1 that minimize this function. And the values that we're going to get are going to be the same expressions that we just solved for. How do you solve for this? That is some calculus. You get your first order conditions, your second order conditions, and your expressions for beta naught hat, beta 1 hat come from that. Let's real quick go over the first order conditions. We have two of them because we have two. We are minimizing with respect to two variables. The first order condition is -2 times the sum from I equals 1 to n yi minus beta naught minus beta 1 times xi, right? The second is -2 times the sum from I equals 1 to n xi times yi minus beta naught minus, let's see. Yes, we'll use the betas now. Hat, 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 xi. These are first order conditions, so we set them equal to 0. And observe that these are the sample counterparts to the population moments that we started with to come up with our expressions for beta naught hat, beta 1 hat, except that we have 2's in front of these instead of 1 over n. But as we showed, these will not matter for the solution of beta naught hat and beta 1 hat because it will show up on both sides of the equation and therefore not matter for the solution of beta naught hat and beta 1 hat. Now, a first order condition is a sufficient but not is a necessary but not sufficient condition for a minimum. You also need to show in the second order condition that the second order conditions are positive, or you can prove that the values for beta naught hat and beta 1 hat equal to b0 and b1 are what minimize this function, and in the text is a great way to show that. So please refer to the text on a way to prove, a way to show that this reaches a